Welcome to solverfy.
Okay, so this question is referring to something that can be derived from the Arrhenius equation, which is that K is equal to A times E to the negative EA over RT, where K is our rate constant, A is our pre-exponential factor, EA is our activation energy, R is the gas constant, and T is the temperature. And from this equation and from known, if we know about two particular rate constants at two different temperatures and utilizing information by looking at graphs and where lines intercept, we can derive the equation that the natural log of the first rate constant over the second rate constant is equal to the activation energy over RT times 1 over temperature 2 in Kelvin minus 1 over temperature 1 in Kelvin. So this is the equation you'd be working from with this kind of problem. And from here, it's almost quite literally just plugging in the rate constants and plugging in the temperatures, and then finally solving for EA, right? I guess you would also plug in sorry, the temperature does not go here. This is just R. Right, so you've got the temperature right here. Okay. One thing to note is that I did say that these have to be in Kelvin, right? And the temperatures were given to you in Celsius, right? So let's start by saying, well, K1 equals 1.27 times 10 to the negative 4 seconds inverse. That's the data they gave us. T1, they told us, is 25 degrees C. So in Kelvin, we have to add 273.15, and we will get 298.15. Okay, K2 is 0.235 seconds inverse, and they told us that the temperature 2 is 75 degrees C. So T2 is going to be, well, it'll be T1 plus 50 degrees. It ends up being, sorry, not 2, 348.15 Kelvin. Okay. Really all that's left now is to plug these numbers in and solve for T1 and T2. Now you can plug them in directly and then solve for EA. Sorry, not T1 and T2, solve for EA. Or you could get everything to one side of the equation before plugging anything in. I think that's probably a good way to do it. So using algebra, that would include multiplying both sides of the equation by R to get rid of the R in the denominator here, and then dividing both sides of the equation by everything in the parentheses there. So divided by 1 over T2 minus 1 over T1. I'm going to divide this side also by 1 over T2 minus 1 over T1. This is supposed to be a 1. Clean that up a little bit. That should just be a 1 over T1. Okay. So I will get on the left-hand side R times ln K1 over K2. And the denominator will be 1 over T2 minus 1 over T1. And that'll all be equal to the activation energy. Okay. So all that's left now is to plug our values in. So it'll be R, which is 8.314 times 10 to negative 3 joules per mole per Kelvin. Oops, should probably get that a little better. Joules per mole per Kelvin. Then the natural log of, and we have a fraction, K1 over K2, so 1.27 times 10 to the negative 4 divided by 0.235. These are in seconds inverse, so the units will cancel. And then this whole thing will be divided by 1 over T2 is 348.15 minus 1 over T1, which was 298.15. Okay, and at this point, we just need to plug this into our calculator, which I will do off to the side so I can report to you a final answer. Just a moment. I'm not sure. Sorry, I made a this would be either this should be 8.314 joules or 8.314 times 10 to the negative 3 kilojoules. All right, it's and they're asking for the asking for things in kilojoules, so I just forgot to put the K there for kilojoules. Okay, now into the calculator. So up top, we'll get 8.314 times 10 to the negative 3. Multiply that times the natural log of 1.27 times 10 to the negative 4 divided by 0.235. And all of that is going to be divided by 1 over 348.15 minus 298.15, or 1 over 298.15, I should say. And we get 129.8. How many sig figs should we have? It looks like we should have, the rate constants imply 3 sig figs. If the temperatures are exact beyond there, yeah, it's probably going to want, this should be 130 kilojoules per mole. Exactly.